Okay, welcome to another episode. So basically today we'll be talking about design of laterally unrestrained beams. And laterally unrestrained beams are beams that are subjected to LTD. I think that's lateral-torsional buckle, and this is under design of steel beam. So quickly I'll be going through like the solvings and like a brief recap of some strength of materials topics like shear force and bending moment, calculation of reactions. So if you look at this diagram now, this is the bending moment equation, and this is the deflection equation. So basically we're making use of this during the course of our solvings, and these are the steps that we'll follow. That is, first of all, you have to calculate the shear force and bending moment of the beam that you are being given. Also, you have to select the best section. That is, you're going to select our best section from the steel designer's manual, which is one of the materials I'll be using for this video, and also BS 5950, that's design of steel structures steel design manual. Then also going to be calculating for the moment capacity. You can calculate moment capacity before you select your best section. Either way, it's anyone that works for you. Then you check for your shear, you check for your deflection, and then you check for your bearing, buckling, and stiffness, and so on and so forth. So the first question we are going to be starting with is this beam. You have like this is 15 kilonewton meter, I think per meter, sorry. And then this is there's a point load here, 35 kilonewton, and from here to here we have that it is 1.5, and from here to here we have 96.5. So I'm not going to be calculating the reactions because we basically all know how to do that. RA is equal to 66.56 kilonewton, and this is 88.44 kilonewton. So I'm just going to show you how to calculate the shear force and bending moment diagram. But just a quick recap: how do you know that your reaction is correct? You can do your reaction check. It's just my way of doing it quickly. That's 66.56 minus 15 times 8, because this UDL is throughout the length. 15 times 8, we have 120 minus 120. This is negative because it's going down. This is positive because it is going up. So minus 35 kilonewton, and then this is going up, plus 88.44 kilonewton. So this should all sum up to give us 0. So let's check it here. 66.56 minus 120 minus 35 plus 88.44, 0. Okay, so we know that we are right on track. So we move on to calculating the shear force and the bending moment diagram. Sorry, this is not part. Okay, so let's draw the beam again. You know, UDL down to the end. We have 35 kilonewton. You know, we have this. RA is equal to 66.56 kilonewton. RB is equal to 88.44 kilonewton. Let's just draw this way, like this. Just down. Mind you, this is the shear force diagram we're doing now. Let's put this as our neutral point, 0. So 0, 0. So we have this going up by 66.56 kilonewton, and then at this point it also encounters a UDL, so it is going to slope down. So by the UDL is 120, so what you're going to do is going down by 120, but you're not going to make that mistake. What you're going to do, you know, from here to here is 6.5 meters, and from here to here is 1.5 meters. So because you have this 35 kilonewton in the middle, there's going to be like a shift in the shear force diagram. So what I do, or what you are meant to do, is that you're meant to split this UDL. Although this place is still 15 kilonewton, this place is still 15 kilonewton, but the distance are different, but it is actually the same thing we are doing. We are just splitting it in half. So we are going to do 15 times 6.5, 15 here times 6.5, which is going to give us 97.5. So this is 66.56 going down by 97.5. So 66.56 minus that answer we got, we are going to get 30.94. So I'm just going to take this and take it down. What did you get here? 30.94. Let's see. There it is. Then put here negative 30.94 kilonewton. Then it encounters this 35 kilonewton down. So still minus 35, which is equal to 65.94. So it goes down further and you get minus 65.94 kilonewton. Remember, we still have another UDL here, so that this is 15 times 1.5. So 15, okay, let me cross check this. 15 times 1.5, so we get 22.5. So we're going to be adding it to 65.94 because it's still going down to 65.94 because it's 8.4. Remember, this is not going straight because it's not a point load, it's going to go this way. So this is 8.4 kilonewton. Remember, we also have RB going this way, it's 8.4 kilonewton. Oh, that's 0, we get 0 here. So that is your shear force diagram. Now for the bending moment diagram, it's very important that you understand the area of shapes as well as how to use similar triangles, because these are triangles that we are going to be dealing with. And mind you, you will need to note that the distance from here to here is not the same as the distance from here to here. So we are going to be determining the length of this and the length of this using similar triangles. How do we do that? Because even when you are calculating you're drawing your moment diagram from your shear force diagram, you calculate the area of the shapes. Then this is a triangle, so this is triangle 1, this is triangle 2, this is another triangle here, triangle 3. We're going to be doing it step by step, and this is a square, which is number 4. So this is going to help us in drawing our shear force our bending moment diagram. But the main thing that we need is the maximum moment, and you know that when shear force is equal to 0, you have your maximum moment. So you might begin to ask, okay, what are we doing? First of all, let's use similar triangles. Let's take note of this place here. This is a triangle too, Abby. You agree with me? So just by the side, we're going to do something here now. Let's take a look at this whole big triangle just from here to here like this. We know that from here to here is 6.5 here. Let's put 6.5 over, still taking at this triangle. Now what is the distance from here to here? We already have that the distance from here to here is 66.56 plus, what's the distance from here to here? The distance from here to here is 30.94, although it's negative, but we are just going to be working with it positively because we need this place. 30.94, don't mind my handwriting, is equal to, we are looking for here to here, Abby, x over here to here, 66.56. So x automatically becomes 6.5 times 66.56, which is equal to this, divided by 66.56 plus 30.94. Our x becomes 4.44 approximately, 4.44 meters. Here is 4.44 meters, and then you know this is 6.5 minus 6.5, you get 2.06 meters. 0. So we all understand that. So now we are going to start calculating the area. So the area of these shapes, now let's start from 1. This is a triangle, which is 1 over 2 a plus b, sorry, 1 over 2 base times height, rather 1 over 2 times base, 4.4, times height, 66.56, and we will get 147.8. So you realize that this area, this place is 147.8, this whole distance. So this one is coming down by like, it will be a curve though. It's right here. So we already have that maximum point. We have here as 147.8. So when you start taking the area, you realize that area of these places will be negative because it's here. So it starts to go up. So your bending moment diagram is something like this. Let's just do for the rest of the shape. For shape 2, you have 1 over 2 times 2.06 times 30.94, which is equal to 32.87. And then for shape 3, you have 1 over 2 times 1.5 times 22.5. So how did we get this 22.5? We know from here to here is 1.5. That's settled. This 22.5, you need from here to here. So what we just did is it's 8.4. This is negative. It's 8.4 minus 65.94. We get the distance from here to here. So we got 22, which is equal to 16.875. Then your triangle. You know what's the distance from here to here? That's 65.94. So your foot is equal to 1.5 times 65.94, which is equal to 98.1. So you just label it, shape force, bend moment diagram. These ones, they are negative, negative, negative. So we see that this place drastically, you minus 147.8 minus 32.87. So 147.8 minus 32.87, it gives us, like, let's see here, is it here? Sorry, somewhere around here, 114.93 minus, that's these two shapes now, 16.875 minus 98.1 approximately gives us 0. So this place is coming back to 0. I hope you understand. So like I said, our maximum bending moment occurs when our shear force is 0. So shear force is 0. So M max is equal to 147.8 kilonewton. Okay, so we got our moment obviously as 147.8 kilonewton meter. So I'm just going to write that here. M is equal to 147.8 kilonewton meter. Here, confirm the newton meter. So how do we select the best section? First of all, select a suitable section to satisfy the bending, shear, and deflection criteria. That's what the question is actually asking us for. I forgot to state that earlier. So we've determined, like we did earlier, we've calculated the shear force and bending moment. So we are going to be selecting our best section and then calculate the moment capacity and check for bending. We've calculated the maximum bending moment. So how do we get our moment capacity? Moment capacity, MC, is equal to our design strength times our plastic modulus. How do we get our design strength from? Now, they said the grade of steel we should use is S275. If you would go to the BS 5950, just go to page 25, you will see a table. This table here, as seen on the screen, you see grade of steel S275, and then they said that the thickness is 9.6 mm. When you say thickness 9.6 mm, but you can see that the thickness here is ranging from 16 to 150. So you know that anything less than 16, that is where you will find your 9.6 mm. If the thickness that they give to you is like 20, you know that that 20 is not inside 16 anymore, it is inside 14. So the design strength you'll be picking is 265. But since that what they gave us is thickness as 9.6 mm, you know that 9.6 is inside this 16 mm thickness, then you will pick your design strength of 275. That's how we got design strength 275 newton per millimeter square. Take note of this unit because we are going to be doing a lot of conversion from millimeter square to meter square. So how do we select our best section? You are going to be selecting your best section from the Steel Designer's Manual. If you would, I would show it on the screen now. I'm in page 1169. I stated it earlier here. I said that your Steel Designer's Manual, pages 166 and pages 169. So okay, let's go to page 169 first. Let's work with page 169. So let me just put it here, page 169.